Hello and welcome to the Sleepless Science Nerd. Tonight we're stepping into the mysterious quiet world of black holes, a place where space and time bend like soft fabric, where light itself cannot escape, and where the very concepts of here and there begin to lose their meaning. It's a realm where gravity reigns supreme, pulling everything matter energy, even the flow of time into its patient and inexorable embrace. These cosmic enigmas sit in the darkness between stars, warping reality itself in ways that unfold one patient moment at a time. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating in the process. Not the worst way to spend a sleepless night. Before we begin, if you enjoy drifting off to the gentle hum of science, I'd be very grateful if you tap the like button and subscribe to the channel. It helps more sleepy minds find their way here. And while you're settling in, I'd love to know where you're watching from and what time it is for you right now. Feel free to share it in the comments. It's always wonderful to see how far these quiet little journeys reach. So get cozy. Let your shoulders relax. Let your thoughts slow down like light approaching the event horizon. Gradually, peacefully, until time itself seems to stretch and soften. Let's begin. Where the light disappears. Picture this. You're standing outside, on a clear night, looking up at the stars. Each pinprick of light has traveled millions, sometimes billions of miles to reach your eyes. Light from distant suns, crossing the vast emptiness of space, carrying stories of worlds we'll never see. But what if I told you that somewhere out there, in the cosmic darkness, there are places where light itself cannot escape? Places so strange that they challenge everything we think we know about the universe. These aren't just dark corners of space. They're regions where the very fabric of reality has been twisted beyond recognition. Imagine a cosmic magician performing the ultimate disappearing act, making light itself vanish without a trace. Not absorbed, not reflected, not scattered. Simply gone, as if it never existed at all. The ancient Greeks had a word for the absence of light. Skotos. Darkness. But what we're talking about goes deeper than darkness. It's the absence of the possibility of light. It's like a cosmic delete button, erasing photons from existence, the moment they venture too close. This is where our journey begins, at the edge of the visible universe, where light meets its match. You might wonder how we can study something that by definition cannot be seen. It's like trying to understand the shape of a room by feeling around in absolute darkness. Scientists have become cosmic detectives, learning to read the clues that these invisible giants leave behind. They watch how stars dance around empty space, how gas glows as it spirals into nothingness, how the very geometry of space-time bends and warps. Think of it this way. If you've ever watched water swirl down a drain, you've seen something similar to what happens around these cosmic mysteries. The water accelerates as it approaches the drain, spinning faster and faster, until it disappears from view. But unlike a drain which simply leads to your home's plumbing, these cosmic whirlpools lead to places where our understanding of physics breaks down entirely. The story of how light disappears begins with a simple question that kept scientists awake at night. What happens when gravity becomes so strong that not even light can escape? It's a question that would lead us down a rabbit hole of discovery, revealing truths about the universe that are stranger than any science fiction story ever written. In the 18th century, a brilliant reverend named John Michel wondered about this very thing. He imagined what he called dark stars, objects so massive that light couldn't escape their gravitational pull. He was thinking of light as tiny particles, little bullets of illumination that could be slowed down and captured like butterflies in a net. He didn't know about the wave nature of light, or about the strange relationship between space and time, but his intuition was pointing towards something profound. Michel's dark stars were mathematical curiosities, theoretical playthings for scientists to ponder. But as our understanding of the universe deepened, these imaginary objects began to seem less like fantasy and more like inevitable consequences of the laws of physics. The universe, it turned out, had a sense of drama. It didn't just allow these cosmic light thieves to exist, it practically demanded their existence. And that brings us to the heart of our cosmic mystery. These aren't just places where light disappears. They're places where the normal rules of existence bend and break. They're laboratories where the universe experiments with the most extreme conditions imaginable. They're cosmic time machines, gravitational lenses, and reality distorters, all rolled into one. As we stand here under the starlit sky, it's humbling to realize that some of those points of light we see are actually dancing around invisible partners, cosmic phantoms that shape the structure of galaxies, the flow of time, and the very fabric of space itself. They're hidden in plain sight, these cosmic magicians performing their ultimate disappearing act on the grandest stage of all, the collapse of a dying star. Every star is engaged in a cosmic battle that defines its entire existence. It's a war between two fundamental forces, the outward pressure of nuclear fusion trying to blow the star apart, and the inward pull of gravity trying to crush it into nothing. For most of a star's life, this battle reaches a delicate balance, a cosmic détente, where neither side can claim victory. Imagine a star as a magnificent cosmic balloon, inflated not with air but with the tremendous pressure of nuclear fire. In its core, temperatures reach millions of degrees, hot enough to fuse hydrogen into helium, releasing energy that pushes outward against the star's own gravitational pull. It's like a perpetual explosion held in check by an invisible hand. This nuclear furnace has been burning for billions of years, steadily converting mass into energy, light, and heat. But here's the thing about battles: they don't last forever. Even the most massive stars eventually run out of fuel. It's like watching a campfire slowly consume all the wood until only embers remain. Except in this case, when the fire dies, something extraordinary happens. The star doesn't just fade away quietly into the night. When a star, 8 times more massive than our sun, exhausts its nuclear fuel, gravity finally wins the cosmic war. But it doesn't win gently. It wins catastrophically. The star's core, no longer supported by the outward pressure of fusion, begins to collapse. And when we say collapse, we mean it in the most dramatic way possible. The core, which might have been the size of Earth, crushes down to something the size of a city in less than a second. Think about that for a moment. An object the size of our entire planet, condensed into something you could drive across in an hour, and it happens faster than you can blink. The gravitational forces involved are so intense that they overwhelm every other force in nature. It's like the universe has suddenly decided to play by different rules. This collapse triggers what astronomers call a supernova, one of the most violent events in the universe. The outer layers of the star, suddenly deprived of their support, crash inward at speeds approaching 30,000 kilometers per second. When this falling material hits the incredibly dense core, it bounces back outward in a spectacular explosion that can outshine an entire galaxy. But here's where our story takes an interesting turn. While the outer layers of the star are blown into space, creating beautiful nebula and seeding the universe with heavy elements, the core continues its relentless collapse. If the core is massive enough, more than about 3 times the mass of our sun, nothing can stop it. Not the strong nuclear force that holds atomic nuclei together, not the electromagnetic force that keeps electrons in their orbits, not even the strange quantum pressure that normally prevents matter from occupying the same space. The collapse becomes what physicists call a runaway process. The more the core shrinks, the stronger its gravitational field becomes. The stronger the field becomes, the faster the collapse proceeds. It's like a cosmic feedback loop, spiraling toward an inevitable conclusion. The matter in the core becomes denser than anything we can imagine on Earth. Denser than the nucleus of an atom. Denser than the heart of a neutron star. Scientists describe this process with a mixture of awe and mathematical precision. The equations that govern stellar collapse read like poetry written in the language of physics. They speak of event horizons and singularities, of spacetime curvature and gravitational time dilation. But beneath all the technical terminology lies a simple, profound truth. We're witnessing the universe's most dramatic transformation. The dying star doesn't just disappear. It becomes something entirely new. It becomes a region of space, where the normal rules of physics are stretched to their breaking point. It becomes a place where time flows differently, where space itself is curved beyond recognition, where matter and energy can check in, but never check out. As the core collapses past a critical threshold, something remarkable happens. The gravitational field becomes so intense that it begins to trap light itself. The boundary where this occurs is invisible, marked only by the point where photons can no longer escape. It's like watching a cosmic curtain fall, hiding the final act of stellar collapse from the rest of the universe. And so, from the death of a star, something entirely new is born. Not a star, not a planet, not even ordinary matter, as we know it. Something that exists in the space between existence and non-existence, between the visible and the invisible, between the known and the unknowable. The collapsed core has become a gateway to regions of reality that challenge our deepest understanding of what it means to exist. The event horizon. Point of no return. There's a moment in every journey where you cross a line from which there's no return. Maybe it's the moment you say I love you for the first time, or when you step off a diving board, or when you commit to a path that will change your life forever. In the cosmos, there's an ultimate version of this moment, a boundary more final than any other in the universe. Imagine standing at the edge of a waterfall, watching the river flow past you. There's a point where the water goes from flowing normally to plunging over the edge, never to return upstream. The event horizon is like that edge, but instead of water, it's the boundary where space and time themselves take a one-way plunge into the unknown. The term event horizon sounds almost poetic, doesn't it? It was coined by physicist Wolfgang Rindler in the 1950s, inspired by the nautical concept of the horizon, the line where the sky meets the sea. But this cosmic horizon is far more profound than any earthly boundary. It's the point where events can no longer communicate with the outside universe. It's where information goes to die, where cause and effect become strange and twisted. Think of the event horizon as the universe's most perfect one-way mirror. From the outside you can see things approach it, but you can never see what happens after they cross. It's like watching someone walk through a door that only opens inward. You can see them approach, you can see them reach the threshold, but once they step through, they might as well have ceased to exist from your perspective. The size of this boundary depends on the mass of the collapsed star. For a typical stellar mass black hole, the event horizon might be about 30 kilometers across, roughly the size of a large city. But don't let that fool you into thinking it's a physical surface. There's no wall there, no membrane, no visible boundary. It's more like an invisible line drawn in the fabric of space-time itself. If you were falling toward this boundary, you wouldn't feel anything special as you crossed it. There would be no sensation of passing through, no cosmic alarm bells, no dramatic moment of transition. From your perspective, space would still look like space, and time would still flow normally. You might notice that the stars behind you appear to be shifting color, becoming redder as their light struggles to escape the intense gravitational field. But otherwise, the crossing would be remarkably unremarkable. But here's where things get truly strange. While you experience the crossing as perfectly normal, anyone watching from far away would see something very different. As you approach the event horizon, time dilation would cause you to appear to slow down from their perspective. Your movements would become sluggish, like someone playing a movie in slow motion. The light from your body would become redder and dimmer as it fights against the gravitational field to escape. To the outside observer, you would appear to freeze at the event horizon, your image becoming fainter and redder until it fades into the cosmic background radiation. From their perspective, you would never actually cross the boundary. You would remain forever suspended at the edge, like a photograph slowly fading away. But from your perspective, you would have crossed long ago, continuing your journey into the unknown regions beyond. This strange disagreement between perspectives reveals something profound about the nature of reality itself. There's no single, universal truth about what happens at the event horizon. The story depends on who's telling it, on where they're standing in the cosmic theater. It's as if the universe has multiple versions of the same story, each equally valid, each equally true from its own perspective. The event horizon acts like a cosmic information filter. Information can flow in, but it can never flow out. It's like a library where books can be deposited but never withdrawn, where knowledge accumulates but can never be retrieved. This creates what physicists call an information paradox, a fundamental question about whether information can truly be destroyed or whether it's somehow preserved in ways we don't yet understand. Scientists have spent decades trying to understand the true nature of this boundary. Some propose that it's not as smooth as it appears, that quantum effects might create a firewall of intense radiation at the horizon. Others suggest that the boundary itself might be an illusion, an artifact of our limited perspective from the outside. These debates rage on in the halls of physics departments around the world, with brilliant minds offering competing theories about what really happens at the edge of the unknown. What makes the event horizon so fascinating is that it represents a fundamental limit to human knowledge. It's a boundary beyond which we can never directly observe, never send back reports, never confirm our theories with direct evidence. It's the ultimate frontier, not just of space, but of knowability itself. It challenges us to think about the nature of existence, the limits of science, and the strange ways that reality can bend and twist under extreme conditions. How gravity bends reality. We live our lives thinking of gravity as a gentle, predictable force. It keeps our feet to the ground, makes apples fall from trees, and gives weight to the world around us. But gravity is actually the universe's master of disguise. What feels like a simple downward pull is actually something far more profound and mysterious. Albert Einstein had a revolutionary insight that changed our understanding of gravity forever. He realized that gravity isn't really a force at all. It's the curvature of space and time themselves. Imagine you're walking on a perfectly flat surface, and suddenly you encounter a hill. You don't feel a mysterious force pushing you sideways. You simply follow the curved path of the hillside. In Einstein's vision, massive objects like stars and planets create hills and valleys in the fabric of space-time, and what we call gravity is just matter following the curved paths through this cosmic landscape. This might sound like abstract physics, but it's actually the most accurate description of reality we have. When you drop a ball, it doesn't fall because Earth is pulling it downward. It falls because Earth's mass has curved the space around it, and the ball is simply following the straightest possible path through that curved space, which happens to lead toward Earth's center. Now imagine what happens when you have an object so massive and so compact that it creates not just a gentle hill in space-time, but a cosmic cliff, a place where the curvature becomes so extreme that it creates a one-way slide into infinity. This is what happens when a massive star collapses into a black hole. The curvature of space-time becomes so severe that it creates a region from which nothing can escape. Think of space-time as a vast rubber sheet stretched tight. If you place a bowling ball in the center, it creates a depression. A marble rolled across the sheet will curve around the depression, mimicking the orbital motion of planets around the sun. But what happens if you replace the bowling ball with something infinitely heavy? The sheet doesn't just dip, it creates a bottomless pit, a tear in the fabric itself. This warping of space-time isn't just a metaphor, it's measurable, observable reality. Scientists have detected gravitational waves, ripples in space-time itself, created when two black holes spiral around each other and merge. These ripples are so tiny that they change the distance between points by less than 1/10,000th the width of a proton. Yet we can measure them with incredible precision using laser interferometry. The curvature of space-time around a black hole creates effects that seem almost magical. Light bends as it passes near the black hole, creating gravitational lensing that can make distant objects appear brighter, larger, or even multiply them into multiple images. It's like having a cosmic magnifying glass that can reveal galaxies that would otherwise be too faint to see. But the most mind-bending effect is how this curvature affects time itself. The stronger the gravitational field, the slower time flows relative to regions of weaker gravity. Near a black hole, this effect becomes extreme. What physicists call gravitational time dilation means that time literally runs slower the closer you get to the black hole's event horizon. If you could somehow hover just above the event horizon of a black hole and watch the universe around you, you would see time speed up everywhere else. Stars would be born and die in what seems like moments. Galaxies would evolve and change before your eyes. The entire universe would age around you while you remained relatively unchanged. It's like being given a cosmic remote control that lets you fast forward through the history of the universe. This time dilation creates one of the most profound paradoxes in physics. From the perspective of someone falling into a black hole, the journey across the event horizon happens in finite time, but from the perspective of someone watching from far away, the falling person appears to slow down and freeze at the horizon, never quite crossing it. Both perspectives are correct. They're just experiencing different versions of the same reality. The extreme curvature of space-time near a black hole also creates what scientists call tidal forces. These aren't the gentle tides we see in Earth's oceans, but violent stretching forces that arise because gravity is slightly stronger on the side of an object that's closer to the black hole. For a person falling feet first toward a black hole, their feet would experience stronger gravitational pull than their head, stretching them vertically while compressing them horizontally. Physicists have given this process the whimsical name spaghettification. What makes all of this so remarkable is that these aren't just theoretical predictions, they're observable realities. We've seen stars torn apart by tidal forces as they ventured too close to black holes. We've measured the gravitational redshift of light climbing out of deep gravitational wells. We've detected the warping of spacetime as massive objects accelerate through it. The story of how gravity bends reality is ultimately a story about the malleability of existence itself. Space and time, which seem so solid and immutable in our everyday experience, are actually fluid, flexible, and responsive to the presence of matter and energy. Black holes are the universe's most extreme artists, sculpting space-time into shapes so radical that they challenge our basic assumptions about what it means to exist. Time slows near the edge. Time is perhaps the most mysterious aspect of our existence. We feel it flowing around us like an invisible river, carrying us from past to future in what seems like an unstoppable current. But near the edge of a black hole, this familiar river becomes something strange and wonderful. A cosmic waterfall, where time itself cascades toward infinity. Imagine you're wearing a watch and standing at a safe distance from a black hole, watching a friend who's decided to take a daring journey closer to the event horizon. As your friend approaches that invisible boundary, something extraordinary begins to happen. From your perspective, their watch starts to tick more slowly. Their movements become languid, like someone swimming through honey. Their voice deepens and stretches, words becoming longer and more drawn out. This isn't science fiction, it's one of the most precisely tested predictions of Einstein's theory of relativity. Time dilation near massive objects is so well established that we have to account for it in GPS satellites. The satellites orbit Earth at a high altitude where gravity is slightly weaker, so their clocks run about 38 microseconds faster per day than clocks on Earth's surface. Without correcting for this effect, your GPS would be off by miles. But near a black hole, time dilation becomes dramatically more extreme. The effect grows stronger as you approach the event horizon, reaching infinite proportions right at the boundary. If you could somehow hover just 1 meter above the event horizon of a typical stellar mass black hole, time would flow about 22% slower than it does far away. Move to just 1 centimeter above the horizon, and time would slow to about 3% of its normal rate. This creates a profound paradox that has puzzled physicists for decades. From the perspective of someone falling into the black hole, their journey across the event horizon takes a finite amount of time, perhaps just a few seconds or minutes. They experience time flowing normally from their own perspective. But from the perspective of someone watching from far away, the falling person appears to slow down as they approach the horizon, eventually seeming to freeze at the boundary. The falling person's light becomes increasingly redshifted as it climbs out of the black hole's gravitational well. What started as normal visible light gradually shifts toward the infrared, then radio waves becoming fainter and fainter, until it fades below the threshold of detection. To the outside observer, the person seems to become a ghost, their image growing dimmer and redder, until it disappears entirely into the cosmic background radiation. This leads to one of the most mind-bending aspects of black hole physics. The same event can have two completely different, yet equally valid descriptions. The person falls through the event horizon and continues their journey into the black hole's interior, experiencing time normally. But simultaneously, from the outside perspective, they never cross the horizon at all, remaining forever frozen at the edge of the black hole. Both stories are true. This isn't a contradiction, it's a profound insight into the nature of reality itself. The universe doesn't have a single, universal timeline. Instead, time is relative, personal, dependent on where you are and how you're moving through space. Near a black hole, this relativity becomes extreme, creating multiple valid versions of the same events. Scientists have spent years trying to understand what this means for our concept of reality. Some propose that information about the falling person remains encoded on the black hole's event horizon, creating a kind of holographic record of everything that has ever fallen in. Others suggest that the apparent freezing at the horizon is just an illusion, that the person really does cross into the black hole, but the information about their crossing becomes inaccessible to outside observers. The slowing of time near black holes also has implications for space travel and the future of human civilization. If we could somehow harness the extreme time dilation effects near black holes, we might be able to travel to the far future. A journey that takes the traveler a few months could correspond to thousands or millions of years passing in the outside universe. It's like having a time machine that only goes forward, allowing us to skip ahead to see how the story of the universe unfolds. But perhaps the most beautiful aspect of time dilation near black holes is what it reveals about the fundamental nature of time itself. Time isn't the steady, universal tick of a cosmic clock. It's something fluid, malleable, responsive to the presence of matter and energy. Near a black hole, we see time in its most extreme form, stretched and twisted like taffy, revealing hidden aspects of reality that we never suspected. The edge of a black hole is where time goes to dance its strangest dance, where the familiar rhythm of seconds and minutes becomes a cosmic symphony of relativity. It's a place where the universe reveals one of its deepest secrets, that time, like space, is not a fixed stage on which events unfold, but an active participant in the cosmic drama, bending and flowing according to the gravitational choreography of matter and energy. The infinite center, singularity explained. At the heart of every black hole lies perhaps the most mysterious concept in all of physics, the singularity. It's a place where our understanding of reality breaks down completely, where the familiar laws of physics throw up their hands in surrender and declare that they simply don't know what happens next. It's like reaching the edge of a map marked "Here be dragons," except in this case the dragons are made of pure mathematical impossibility. Imagine trying to divide a number by 0 on a calculator. The display might show error or undefined, because mathematics simply doesn't know how to handle such a request. The singularity is the universe's equivalent of that error message, a place where the normal rules of existence encounter something so extreme that they can't process it. According to Einstein's equations, the singularity is a point of infinite density and zero volume at the center of a black hole. This means that all the mass that collapsed to form the black hole is concentrated in a region smaller than the smallest thing you can imagine, smaller than an atom, smaller than a proton, smaller than anything that has physical meaning. It's a point where the curvature of space-time becomes infinite, where the very concepts of here and there lose their meaning. But here's the thing about infinities in physics. They're usually a sign that something is wrong with our theories. Just as a calculator can't really divide by 0, the universe probably can't create truly infinite density. The singularity is more likely a placeholder, a mathematical artifact, that points to the limits of our current understanding, rather than a description of what actually exists. Think of it this way. If you're looking at a distant mountain through a telescope, and the telescope is slightly out of focus, the mountain might appear as a single blurry point. You know there's something there, but you can't make out the details. The singularity might be similar. Our current theories are like that, out-of-focus telescope, showing us something important, but not quite revealing what's actually there. Some physicists believe that quantum mechanics might come to the rescue. At the incredibly small scales and high energies near what we call the singularity, quantum effects might prevent the formation of a true mathematical singularity. Instead of infinite density, there might be some kind of quantum soup, a region where matter and energy exist in states so exotic that we don't have names for them yet. One possibility is that the singularity is replaced by something called a quantum bounce. Instead of collapsing to infinite density, the matter might reach some maximum compression and then bounce back, potentially creating a new region of spacetime or even a new universe. It's like a cosmic trampoline that prevents the ultimate collapse by transforming the inward motion into outward expansion. Another intriguing possibility is that the singularity might be connected to other regions of spacetime through cosmic tunnels called wormholes. If this were true, the matter falling into a black hole might not be destroyed, but transported to distant regions of our universe, or even to other universes entirely. The singularity would become a cosmic transit hub, rather than a point of ultimate destruction. But perhaps the most mind-bending possibility is that the singularity represents a fundamental limit to the concept of space and time themselves. Maybe at the center of a black hole, the smooth fabric of space-time gives way to something more granular, a quantum foam where space and time exist in discrete indivisible units. It would be like discovering that what appears to be a smooth painting is made of individual pixels when you look closely enough. The study of singularities has led physicists to some of the most profound questions about the nature of existence. What does it mean for something to exist if it can't be described by the laws of physics? Can information be truly destroyed? Or does it persist in some form even when matter is crushed beyond recognition? Is there a fundamental limit to how small something can be, or how curved spacetime can become? These questions have inspired decades of research into what physicists call quantum gravity, the search for a theory that can successfully merge Einstein's description of gravity with the quantum mechanical description of the other forces of nature. Such a theory might finally tell us what really happens at the center of a black hole, replacing the mysterious singularity with something more concrete and understandable. Until then, the singularity remains one of the universe's greatest mysteries, a cosmic question mark sitting at the heart of some of the most extreme objects in existence. It's a reminder that despite all our scientific progress, there are still regions of reality that lie beyond our current understanding, waiting to be explored by future generations of scientists and dreamers. The singularity is where the universe keeps its deepest secrets, where the familiar world of cause and effect gives way to something more fundamental and more mysterious. It's a place where mathematics meets its match, where physics encounters its limits, and where the human imagination must stretch to encompass concepts that challenge our most basic assumptions about what it means to exist. Falling forever. What happens if you enter? Let's imagine the unimaginable. You've somehow found yourself falling toward a black hole. Perhaps you're an astronaut on a mission gone wrong. Or maybe you're a cosmic explorer from some distant future when interstellar travel is as common as taking a bus. Either way, you're about to experience the most extreme environment in the universe, and the journey will be unlike anything anyone has ever experienced. Your first surprise might be that the approach feels remarkably normal. Despite what Hollywood movies might suggest, you don't suddenly feel heavier or experience some mysterious force pulling you inward. Instead, you're in free fall, experiencing the same weightlessness that astronauts feel in orbit around Earth. Einstein called this the happiest thought of his life, the realization that someone in free fall doesn't feel gravity at all. As you fall, you might notice that the black hole doesn't look like a hole at all. There's no dark circle against the stars, no obvious boundary marking where safety ends and doom begins. Instead, you see the stars behind you, their light slightly shifted toward the red end of the spectrum due to the black hole's gravitational field. The stars in front of you might appear slightly bluer, their light compressed by your motion toward them. But then, something strange begins to happen. You start to feel a subtle stretching sensation, as if someone is gently pulling on your feet while pressing down on your head. This is the beginning of what physicists call tidal forces, the same forces that cause ocean tides on Earth, but dramatically more intense near a black hole. The stretching occurs because gravity is slightly stronger at your feet, which are closer to the black hole than at your head. This difference is usually negligible, but as you fall deeper into the black hole's gravitational well, the stretching becomes more pronounced. If you're falling feet first, you'll be stretched vertically while being compressed horizontally, gradually assuming the shape of a tall, thin noodle. This process, which physicists have playfully dubbed spaghettification, would eventually become fatal for any real person. But let's imagine you're made of some incredibly strong material that can survive the stretch. In that case, you might experience one of the most profound journeys possible, a voyage to the very edge of known physics. As you approach the event horizon, you might notice something odd about the passage of time. If you could somehow look back at the universe you left behind, you would see it speeding up. Stars would be born and die in what seems like moments. Galaxies would evolve and change before your eyes. The entire cosmic story would accelerate around you, as if you were watching a movie in fast forward. This happens because of gravitational time dilation. Time flows more slowly in stronger gravitational fields, so as you fall deeper into the black hole's influence, time appears to speed up everywhere else. You're essentially being given a glimpse of the universe's future, watching eons pass in what feels like minutes or hours. When you finally cross the event horizon, you might expect some dramatic moment, a flash of light, a sudden change in the environment, some cosmic fanfare to mark your passage into the unknown. But there would be nothing. The crossing would be remarkably unremarkable. Space would still look like space. Time would still flow normally, from your perspective, and you would continue your journey inward without any obvious sign that you've passed the point of no return. This is one of the most counterintuitive aspects of black hole physics. The event horizon isn't a physical barrier, it's more like an invisible line in space-time. From your perspective, there's nothing special about it. You wouldn't know you've crossed it until you try to send a signal back to the outside universe, and realize that your message can never reach its destination. As you continue falling inward, The tidal forces would continue to strengthen, the stretching would become more and more severe, eventually reaching a point where even the strongest materials would be torn apart. Your atoms would be stretched and compressed, your very molecular structure reshaped by the extreme gravitational gradients. But here's where the story becomes truly mysterious. What happens in the final moments of your fall depends on theories that haven't been fully developed yet. Some physicists suggest that you might encounter a firewall of intense radiation just inside the event horizon. Others propose that you might find yourself in a region where space and time behave in ways that are impossible to describe with our current understanding of physics. If you somehow survived all the way to the center of the black hole, you would encounter the singularity, that mysterious point where the laws of physics break down completely. What happens there is anyone's guess. You might be crushed out of existence, or you might find yourself in some other region of space-time entirely. You might encounter physics so exotic that it would redefine our understanding of reality itself. The journey into a black hole is ultimately a journey into the unknown. It's a voyage that pushes the boundaries of human knowledge and imagination, taking us to places where the familiar world of cause and effect gives way to something more fundamental and more mysterious. It's a reminder that the universe still holds secrets that we're only beginning to understand, and that the most extreme environments can teach us the most profound lessons about the nature of existence itself. Not a hole, not even black. The name black hole is one of the most misleading terms in all of science. It suggests a dark void, an empty space, a cosmic drain where things simply disappear. But these mysterious objects are neither holes nor truly black. They're something far more interesting and complex than their name suggests. Let's start with the hole part. When you think of a hole, you probably imagine something like a pit in the ground or a gap in a piece of paper. Essentially an absence of something. But a black hole is quite the opposite. It's a region of space where matter has been compressed to such incredible density that it warps the very fabric of space-time. Rather than being empty, it's the most concentrated collection of mass and energy possible in the universe. Think of it this way. If you could take all the matter in a city and compress it down to the size of a marble, you'd have something approaching the density of a black hole. It's not an absence of matter. It's matter taken to its absolute extreme. The hole is really a region where gravity has become so strong that it creates a one-way boundary in space-time itself, and they're not really black either. This might seem counterintuitive, since by definition black holes don't emit light, but the space around a black hole is often among the brightest regions in the universe. As matter falls toward the black hole, it accelerates to tremendous speeds, heating up and glowing brilliantly. This forms what astronomers call an accretion disk, a swirling maelstrom of superheated gas that can outshine entire galaxies. The accretion disk is like a cosmic whirlpool made of light, gas, and dust, spiral inward, friction heating them to millions of degrees. The material glows with X-rays, gamma rays, and intense visible light. Some of this matter doesn't fall directly into the black hole, but gets flung outward in spectacular jets that can extend for thousands of light years. These jets are among the most powerful phenomena in the universe, capable of affecting the evolution of entire galaxies. Even more surprisingly, black holes themselves might not be truly black. In the 1970s, Stephen Hawking made a revolutionary discovery. Black holes should actually emit radiation. This Hawking radiation arises from quantum effects near the event horizon, where the vacuum of space itself becomes unstable. Virtual particles that normally appear and disappear in microseconds get separated by the black hole's immense gravitational field, with one particle falling in and the other escaping as real radiation. This means that black holes are slowly evaporating, like ice cubes melting in the sun. The process is incredibly slow for large black holes. A black hole with the mass of our sun would take longer than the age of the universe to evaporate completely. But smaller black holes evaporate faster, and in their final moments they might explode in a brilliant flash of gamma rays. The term black hole was actually coined by physicist John Wheeler in 1967, and he later expressed some regret about the name. Before that, scientists called them collapsed stars or frozen stars, names that better captured their true nature. The problem is that once a catchy name sticks in popular culture, it's almost impossible to change. What makes the naming even more ironic is that black holes are actually some of the most dynamic and energetic objects in the universe. They're not passive voids, but active engines of cosmic evolution. They regulate the growth of galaxies, trigger the formation of new stars, and sculpt the large-scale structure of the universe. They're cosmic recyclers, breaking down matter and energy and redistributing them across space and time. The region immediately around a black hole is called the ergosphere, and it's one of the most bizarre places in the universe. Here, space-time itself is dragged around by the black hole's rotation, creating a region where it's impossible to remain stationary. Everything light, matter, even empty space, is forced to rotate along with the black hole. It's like being caught in a cosmic whirlpool where the very fabric of reality is spinning. This dragging of space-time, called frame dragging, creates possibilities that seem almost magical. In theory, you could extract energy from a rotating black hole by dropping objects into the ergosphere and having them interact with the dragged space-time. The objects could emerge with more energy than they started with, powered by the black hole's rotation. It's like having a cosmic battery that you can tap into for nearly unlimited energy. Black holes also challenge our understanding of information and reality. When matter falls into a black hole, what happens to the information that described that matter? Does it disappear forever, or is it somehow preserved? This information paradox has puzzled physicists for decades, and has led to some of the most creative theories in modern physics. Some scientists propose that the information is encoded on the black hole's event horizon in a holographic form. Just as a hologram can store three-dimensional information on a two-dimensional surface, the event horizon might store all the information about everything that has ever fallen into the black hole. This would mean that black holes are like cosmic hard drives, preserving a record of everything they've consumed. Others suggest that the information might be released back into the universe through Hawking radiation, but in such a scrambled form that it's practically impossible to decode. It would be like trying to reconstruct a book from the pattern of smoke rising from a fire where the book was burned. The study of black holes has also revealed deep connections between gravity, thermodynamics, and information theory. Black holes have temperature and entropy, just like any other thermodynamic system. They can be hot or cold, and they contain information in proportion to the area of their event horizon. This suggests that the fundamental nature of space, time, and information might be more deeply connected than we ever imagined. Perhaps most remarkably, black holes might be connected to the very fabric of space-time itself. Some theories suggest that space-time is not continuous, but made up of discrete units, quantum pixels of reality. If this is true, then black holes might be places where we can glimpse the underlying structure of existence itself. So the next time you hear someone talk about black holes, remember that they're not holes, and they're not truly black. They're some of the most complex, dynamic, and mysterious objects in the universe. Cosmic laboratories where the laws of physics are pushed to their absolute limits, revealing truths about reality that we're only beginning to understand. Spaghettification and the stretch of space. There's something almost whimsical about the term spaghettification, as if physicists decided to name one of the universe's most extreme phenomena after a dinner dish. But don't let the playful name fool you. This process reveals something profound about how space itself behaves under the most extreme conditions imaginable. Imagine you're holding a piece of taffy and slowly pulling it apart. At first it stretches uniformly, but as you continue pulling, it begins to narrow in the middle and elongate at the ends. Eventually, it becomes so thin that it snaps. Now imagine that the taffy is made of space-time itself, and you're witnessing what happens when gravity becomes so strong that it literally stretches the fabric of reality. Spaghettification occurs because gravity isn't uniform. It follows what physicists call the inverse square law, meaning that gravitational force decreases with the square of the distance. This sounds technical, but the implications are dramatic. If you're falling feet first toward a black hole, your feet experience slightly stronger gravity than your head, because they're closer to the black hole's center. This difference in gravitational pull creates what we call tidal forces. On Earth, we experience tidal forces too. They're what cause the ocean tides. The moon's gravity pulls slightly more strongly on the water facing it than on the water on the opposite side of Earth. But the difference is gentle, creating the peaceful rhythm of tides that has influenced human culture for millennia. Near a black hole, these same forces become violent and destructive. The stretching begins subtly. At first you might feel like you're on a medieval torture rack, with something pulling gently on your extremities. But as you fall deeper into the black hole's gravitational well, the stretching becomes more pronounced. Your body begins to elongate vertically while being compressed horizontally, gradually assuming the shape that gives this process its pasta-inspired name. But spaghettification isn't just about stretching objects. It's about stretching space itself. Einstein taught us that matter and energy curve, spacetime, and near a black hole, this curvature becomes so extreme that it creates gradients in the fabric of reality. These gradients are what cause the tidal forces, and they reveal something beautiful about the nature of space itself. Think of spacetime as a flowing river. In calm waters, a leaf floating on the surface moves gently downstream, but near a waterfall, the water accelerates and becomes turbulent. Different parts of the leaf experience different flow rates, causing it to stretch and tumble. Near a black hole, space-time flows toward the center like a cosmic waterfall, and anything caught in this flow experiences the stretching effects of the varying current. The strength of spaghettification depends on the size of the black hole. Counterintuitively, smaller black holes create stronger tidal forces than larger ones. This is because the event horizon of a smaller black hole is closer to its center, where the gravitational field is most intense. For a black hole with the mass of our Sun, the tidal forces would be lethal long before you reach the event horizon. But for a supermassive black hole, one with millions or billions of times the mass of our Sun, you could cross the event horizon and continue falling inward for quite some time, before the stretching became noticeable. This creates one of the strangest paradoxes in black hole physics. The more massive and dangerous a black hole is, the gentler the initial experience of falling into it. It's like the difference between going over Niagara Falls in a barrel versus gently sliding down a massive water slide. The bigger fall is ultimately more dangerous, but the initial experience is more comfortable. Scientists have observed spaghettification in action through telescopes, watching as stars venture too close to black holes and are torn apart by tidal forces. These events, called tidal disruption events, create spectacular displays of light as the star's material is stretched into long streamers that spiral around the black hole. The disrupted star forms an accretion disk, heating up and glowing brilliantly as it falls toward the event horizon. One of the most famous examples was observed in 2020 when astronomers watched a star get shredded by a black hole 215 million light-years away. The star, which had been orbiting the black hole peacefully for perhaps millions of years, finally ventured too close. The black hole's tidal forces overcame the star's own gravity, pulling it apart like cotton candy. The resulting fireworks were visible across the universe, a cosmic lighthouse announcing the star's demise. But spaghettification isn't just about destruction. It's also about transformation. The process reveals how matter and energy behave under the most extreme conditions possible. When a star is spaghettified, its material doesn't just disappear. Instead, it's recycled, transformed into high-energy radiation and exotic particles that can influence the evolution of entire galaxies. The study of spaghettification has also led to insights about the nature of space and time themselves. The fact that space can be stretched and compressed like a physical material suggests that it has properties we're only beginning to understand. Some physicists propose that space-time might be made of discrete units, quantum pixels of reality that can be stretched and twisted under extreme conditions. These ideas connect to some of the most cutting-edge research in theoretical physics, including the study of quantum gravity and the search for a theory of everything that would unify our understanding of all the fundamental forces. The extreme stretching of space-time near black holes provides a natural laboratory for testing these theories under conditions that we could never replicate on Earth. Spaghettification also raises philosophical questions about the nature of identity and existence. If you were gradually stretched over thousands of kilometers, at what point would you cease to be you? When does a collection of particles stop being a person and become something else entirely? These questions might seem abstract, but they touch on fundamental issues about consciousness, identity, and the nature of existence itself. The process reminds us that space and time aren't the fixed, immutable backdrop that they appear to be in our everyday experience. They're dynamic, responsive, and capable of being molded by the presence of matter and energy. Near a black hole, this malleability becomes extreme, creating effects that challenge our basic assumptions about the nature of reality. Can anything escape a black hole? For decades, the answer to this question seemed absolutely clear. Nothing can escape a black hole. By definition, the event horizon marks the boundary beyond which escape is impossible. It's like a cosmic one-way street with no exit ramps, no U-turns, no way back to the world of light and possibility. But science has a way of challenging our assumptions, and the story of black hole escape is more nuanced and surprising than it first appears. The classical answer is still mostly correct. Once something crosses the event horizon, it cannot escape in the conventional sense. This isn't due to some mysterious force holding things captive. It's a consequence of the geometry of spacetime itself. Inside the event horizon, all paths through spacetime lead inward. Trying to escape would be like trying to go north of the North Pole. It's not forbidden by any force, it's simply a meaningless concept given the geometry of the situation. Imagine you're in a river flowing toward a waterfall. Far upstream, you can easily swim to shore. But as you approach the waterfall, there comes a point where the current becomes too strong. Even if you're an Olympic swimmer, you can't make progress against the flow. The event horizon is like that point of no return, except instead of water flowing toward a waterfall, it's space-time itself flowing toward the black hole's center. But here's where the story gets interesting. In the 1970s, Stephen Hawking discovered that black holes aren't quite as black as their name suggests. Through a process involving quantum mechanics and the strange behavior of empty space, black holes actually emit radiation. This Hawking radiation represents a form of escape, not of things that have fallen in, but of new particles created near the event horizon. The process is subtle and strange. In the quantum world, empty space isn't really empty. It's filled with virtual particles that normally pop into existence and immediately annihilate each other. Near a black hole's event horizon, the extreme gravitational field can separate these particle pairs before they can annihilate. One particle falls into the black hole, while the other escapes as real radiation. From the outside, it appears that the black hole is glowing with thermal radiation. This radiation is incredibly faint for large black holes, fainter than the cosmic microwave background radiation that fills the universe. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero, making it colder than the space around it. But the radiation is real, and it means that black holes are slowly evaporating, like ice cubes melting in a warm room. The process becomes more dramatic for smaller black holes. The temperature of Hawking radiation is inversely proportional to the black hole's mass, so smaller black holes are actually hotter than larger ones. A black hole with the mass of a mountain would glow white hot, and one with the mass of a large asteroid would explode in a brilliant flash of gamma rays. But Hawking radiation raises a profound puzzle. What happens to the information that fell into the black hole? If the black hole eventually evaporates completely, does the information about everything that fell in get destroyed forever? This would violate a fundamental principle of quantum mechanics, which says that information cannot be created or destroyed. This information paradox has led to some of the most creative and controversial ideas in modern physics. Some scientists propose that the information is encoded in the Hawking radiation itself, but in such a scrambled form that it's practically impossible to decode. Others suggest that the information is preserved on the black hole's event horizon in a holographic form, like a cosmic hard drive storing data on its surface. One of the most radical proposals is that black holes might be connected to other regions of space-time through microscopic wormholes. If this were true, matter and information might not be destroyed when they fall into a black hole. They might be transported to distant regions of our universe or even to other universes entirely. The black hole would become a cosmic teleporter rather than a cosmic destroyer. Recent developments in string theory and quantum gravity have suggested even more exotic possibilities. Some physicists propose that the event horizon itself might be an illusion, that what we think of as the inside of a black hole might actually be equivalent to the outside in some deep mathematical sense. This would mean that information never really falls into the black hole at all, but remains accessible to outside observers in a highly encoded form. There's also the possibility of more conventional forms of escape through processes that occur outside the event horizon. Matter spiraling toward a black hole can be accelerated to tremendous speeds, and some of it can be flung outward in powerful jets that extend for thousands of light years. These jets can carry matter and energy far from the black hole, effectively rescuing it from the gravitational prison. The study of black hole escape has also revealed connections to some of the deepest questions in physics. The relationship between gravity, quantum mechanics, and information theory suggests that our understanding of space, time, and reality itself might need to be fundamentally revised. Black holes might be telling us something profound about the nature of existence that we're only beginning to understand. Perhaps most remarkably, the question of black hole escape has led to insights about the nature of the universe itself. Some theories suggest that our entire universe might exist inside a black hole, with what we think of as the Big Bang, actually being the formation of the black hole from some higher dimensional perspective. If this were true, then we ourselves might be examples of information that has escaped from a black hole in some sense. The question of whether anything can escape a black hole ultimately depends on what we mean by escape, and what we mean by anything. While classical objects cannot escape once they cross the event horizon, the quantum world offers more subtle possibilities. Information might escape through Hawking radiation, or it might be preserved in ways that we don't yet understand. Matter might be transformed and transported through exotic processes that we're only beginning to explore. As our understanding of black holes continues to evolve, so too does our understanding of escape. What once seemed like an absolute barrier is now recognized as a boundary that might be more permeable than we initially thought. The story of black hole escape is really the story of how science progresses, by challenging our assumptions, exploring new possibilities, and discovering that the universe is always more subtle and surprising than we imagined. Hawking radiation and the slow fade. In the pantheon of scientific discoveries, few have been as surprising and revolutionary as Stephen Hawking's realization that black holes aren't truly black. In 1974, this brilliant physicist made a discovery that would forever change our understanding of these cosmic monsters. Black holes actually glow with thermal radiation slowly evaporating like morning dew in the rising sun. The story begins with one of the strangest aspects of quantum mechanics: the idea that empty space isn't really empty. What we think of as vacuum is actually a seething foam of virtual particles, pairs of particles and antiparticles, that pop into existence and immediately annihilate each other. These quantum fluctuations are so brief and subtle that they usually have no observable effect on the world around us. But near a black hole, they become the key to understanding how these cosmic giants might eventually fade away. Imagine the space near a black hole's event horizon as a cosmic shoreline where the quantum foam of empty space meets the extreme curvature of space-time. In this turbulent region, something remarkable happens to the virtual particle pairs. The intense gravitational field can separate them before they have a chance to annihilate each other. One particle falls into the black hole, while the other escapes into space as real radiation. This process is incredibly subtle. The escaping particles don't come from inside the black hole. They're created right at the event horizon from the quantum energy of empty space itself. It's as if the black hole is so massive that it can borrow energy from the quantum vacuum, with the debt being paid by the gradual decrease in the black hole's mass. The radiation that emerges has a fascinating property. It's thermal, meaning it has the same character as the heat radiated by any warm object. But the temperature is inversely related to the black hole's mass. Larger black holes are colder, while smaller ones are hot. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. This means that stellar mass black holes are actually absorbing more energy from their surroundings than they emit through Hawking radiation. They're growing, not shrinking, fed by the ambient radiation of the universe. It's only when the universe expands and cools significantly, in about a Google years, that's 1 followed by 100 zeros, that these black holes will begin to lose mass faster than they gain it. But smaller black holes tell a different story. A black hole, with the mass of a large mountain, would glow white hot, radiating with the intensity of a star. One with the mass of a small asteroid would be incredibly bright, and in its final moments, it would explode in a brilliant flash of gamma rays that could outshine galaxies. The evaporation process is paradoxical in its behavior. As a black hole loses mass through Hawking radiation, it becomes smaller and hotter, causing it to radiate even more intensely. This creates a runaway process where the evaporation accelerates as the black hole shrinks. The final moments of a black hole's existence would be spectacular. A cosmic fireworks display marking the end of one of the universe's most extreme objects. But this evaporation process raises profound questions about the nature of information and reality. When matter falls into a black hole, it carries with it information, the quantum states that describe its properties, its history, its very identity. If the black hole eventually evaporates completely through Hawking radiation, what happens to this information? Does it disappear forever? Or is it somehow preserved? This information paradox has puzzled physicists for decades. The principle of unitarity in quantum mechanics insists that information cannot be created or destroyed, only transformed. But if information can be destroyed in black holes, It would force us to abandon one of the most fundamental principles of physics. The stakes couldn't be higher. Our understanding of reality itself hangs in the balance. Some physicists have proposed that the information is actually encoded in the Hawking radiation itself, but in such a scrambled and subtle form that it's practically impossible to decode. Imagine trying to reconstruct a symphony from the random hissing of static. The information might be there, but extracting it would require perfect knowledge of the scrambling process. Others suggest that the information never really falls into the black hole at all. Instead, it might remain encoded on the event horizon in a holographic form, like a cosmic hard drive storing data on its surface. From this perspective, the three-dimensional reality we experience might be an illusion, a holographic projection of information stored on a two-dimensional surface. The study of Hawking radiation has also revealed deep connections between black holes and thermodynamics. Black holes have temperature, entropy, and all the other properties of thermodynamic systems. They can be hot or cold, they can gain or lose energy, and they obey the fundamental laws of thermodynamics. This suggests that black holes might be the key to understanding the relationship between gravity, quantum mechanics, and information theory. Recent developments in string theory and quantum gravity have suggested even more exotic possibilities. Some physicists propose that Hawking radiation might be connected to the internal structure of black holes through microscopic wormholes or other quantum tunnels. Others suggest that the radiation might carry subtle correlations that preserve information in ways we don't yet understand. The implications of Hawking radiation extend far beyond black holes themselves. The process reveals fundamental truths about the nature of space, time, and quantum mechanics. It shows us that the universe is far stranger and more interconnected than we might have imagined, with effects that seem to violate our everyday understanding of causality and locality. Perhaps most remarkably, Hawking radiation suggests that black holes are not eternal. Even the most massive black holes will eventually evaporate, leaving behind only the faintest whisper of radiation. In the far future, when the stars have burned out and the universe has grown cold and dark, the slow glow of evaporating black holes might be the last source of energy in the cosmos. The discovery of Hawking radiation represents one of the most beautiful syntheses in all of physics, bringing together general relativity, quantum mechanics, and thermodynamics in a way that illuminates the deep structure of reality. It reminds us that the universe is full of surprises, that even the most extreme and seemingly permanent objects are subject to change and transformation. As we continue to study black holes and their mysterious radiation, we're not just learning about these cosmic giants, we're discovering fundamental truths about the nature of existence itself. The slow fade of black holes through Hawking radiation is ultimately the story of how the universe transforms and evolves, how information and energy flow through space and time, and how the quantum world influences even the largest structures in the cosmos. Black holes have no hair. Simplicity of the beast. In the world of physics, there's a saying that sounds almost like a cosmic joke: black holes have no hair. This whimsical phrase, coined by physicist John Wheeler, captures one of the most profound and counterintuitive aspects of these mysterious objects. Despite being formed from the collapse of complex stars with intricate magnetic fields, chemical compositions, and detailed structures, black holes emerge from this chaos with startling simplicity. Imagine you took every book in a vast library, millions of volumes containing the sum total of human knowledge, and somehow compressed them all into a single, simple object that could be described with just 3 numbers. That's essentially what happens when a star collapses into a black hole. All the complexity, all the details, all the intricate structure of the original star vanishes, leaving behind something that can be completely characterized by just 3 properties: mass, electric charge, and angular momentum. How fast it's spinning. This idea is formally known as the no-hair theorem, and it represents one of the most striking examples of simplicity emerging from complexity in all of physics. It's as if the universe has a built-in minimalist aesthetic, stripping away all unnecessary details to reveal only the most fundamental characteristics. The mass of a black hole is perhaps the most intuitive of these 3 properties. It determines the strength of the black hole's gravitational field, the size of its event horizon, and how it affects the space-time around it. A black hole with twice the mass has roughly twice the gravitational pull and an event horizon that's twice as large. It's the cosmic equivalent of a celestial body's weight, though in the strange world of general relativity, mass and energy are really the same thing. Electric charge is the second property, though most real black holes are expected to be electrically neutral. This is because the universe tends to maintain electrical neutrality on large scales, and any charged black hole would quickly attract oppositely charged particles from its surroundings until its net charge became zero. A charged black hole would create an electric field extending across space, but this situation is thought to be highly unstable and short-lived in the real universe. The third property, angular momentum or spin, is perhaps the most interesting. Just as a figure skater spins faster when they pull in their arms, a collapsing star spins faster as it shrinks. The conservation of angular momentum means that even a slowly rotating star can become a rapidly spinning black hole. This rotation drags spacetime around with it, creating a region called the ergosphere, where nothing can remain stationary relative to distant observers. What makes the no-hair theorem so remarkable is what it doesn't include. The black hole remembers nothing about the complex magnetic fields of the original star, nothing about its chemical composition, nothing about the intricate patterns of convection in its interior. It doesn't matter if the star was made of hydrogen and helium, or if it had already fused heavier elements in its core. It doesn't matter if the star had a complex magnetic field, or if it was completely unmagnetized. All of this information is lost forever, erased by the violent collapse that created the black hole. This erasure of information creates what physicists call the information paradox. If all the complex details of the original star are lost, what happens to the information that described those details? In quantum mechanics, information cannot be created or destroyed, only transformed. But black holes seem to violate this principle by erasing information completely. It's as if the universe has a cosmic shredder that destroys information rather than just hiding it. The no-hair theorem also has profound implications for our understanding of space and time. It suggests that the event horizon of a black hole is remarkably smooth and featureless, like a perfect sphere or a slightly flattened sphere if the black hole is spinning. There are no bumps, no irregularities, no surface features that might reflect the complex structure of the original star. The event horizon is nature's most perfect surface, smoother than anything we could ever create in a laboratory. But recent developments in physics have begun to challenge this picture of perfect simplicity. Some theorists propose that black holes might have soft hair, subtle quantum effects that could encode information about what has fallen into them. This soft hair wouldn't be visible in the classical sense, but it might be detectable through subtle correlations in the Hawking radiation that black holes emit. The search for black hole hair has become one of the most active areas of research in theoretical physics. Scientists are looking for ways that black holes might store information about their formation and history, perhaps through quantum effects near the event horizon or through connections to other regions of spacetime via microscopic wormholes. One possibility is that the event horizon itself might not be as smooth as it appears. At the quantum level, it might be covered in a subtle fuzz of quantum fluctuations that could encode information about everything that has fallen into the black hole. This quantum fuzz would be far too small to detect directly, but it might leave subtle signatures in the radiation that escapes from the black hole. Another possibility is that black holes might be connected to other regions of spacetime through quantum entanglement. If this were true, the information that falls into a black hole might not be lost, but transferred to these other regions through subtle quantum correlations. The black hole would appear to have no hair from our perspective, but the information would be preserved in a form that we don't yet understand. The study of black hole hair has also revealed connections to some of the deepest questions in physics. The relationship between general relativity and quantum mechanics, the nature of space and time, and the fundamental structure of reality all come together in the question of whether black holes truly have no hair, or whether they might be more complex than they appear. Perhaps most remarkably, the no-hair theorem suggests that black holes might be the universe's ultimate examples of emergent simplicity. Just as a complex system can give rise to simple collective behavior, the incredibly complex process of stellar collapse might give rise to objects of startling simplicity. It's as if the universe has a way of distilling complexity into its most essential components. The phrase "black holes have no hair" reminds us that nature often surprises us with its elegance and simplicity. In a universe full of complexity and chaos, black holes stand as monuments to the power of simple fundamental laws. They show us that even the most extreme and violent processes can give rise to objects of beautiful mathematical simplicity, governed by just a few basic principles. As we continue to study these mysterious objects, we're not just learning about black holes, We're discovering fundamental truths about the nature of information, complexity, and simplicity in the universe. The question of whether black holes truly have no hair is ultimately a question about the deepest structure of reality itself. Do black holes store information? Imagine you're holding a book, perhaps a favorite novel filled with memories and meaning. Now imagine that book somehow fell into a black hole. Where does all that information go? The words, the ideas, the patterns of ink on paper that created meaning. Do they simply vanish from the universe forever? This might seem like an abstract question, but it strikes at the heart of one of physics' most fundamental principles, information conservation. In the quantum world, information is never truly destroyed. It might be scrambled beyond recognition, but it's always preserved somewhere. It's like a cosmic library where books might be torn apart and scattered. But every letter, every punctuation mark, still exists somewhere in the collection. But black holes seem to violate this principle. When matter falls past the event horizon, it appears to be lost forever, and when the black hole eventually evaporates through Hawking radiation, that radiation seems to carry no information about what fell in. It's as if the universe's library is burning books, destroying information that can never be recovered. This puzzle has haunted physicists for decades. Stephen Hawking himself spent much of his later career wrestling with what became known as the information paradox. On one hand, general relativity suggests that information falling into a black hole is simply gone. On the other hand, quantum mechanics insists that information must be preserved. Both theories can't be right, yet both have been tested and verified countless times. Some scientists propose that information isn't actually lost. It's encoded on the black hole's event horizon, like a hologram that records everything that falls in. Picture the event horizon as a cosmic computer hard drive, storing information in patterns so complex we can't yet read them. When the black hole evaporates, this information might be released in the Hawking radiation, but in such a scrambled form that reconstructing the original information would be virtually impossible. Others suggest something even more radical, that black holes might be information processing systems, cosmic computers that transform information rather than destroying it. In this view, what we perceive as matter falling into a black hole might actually be information being processed and transformed into something else entirely. There's also the possibility that our understanding of time itself needs revision. From our perspective, it takes forever for anything to actually cross the event horizon. Time dilation stretches that final moment infinitely. Perhaps the information never actually falls in from the universe's perspective, but remains forever suspended at the edge, encoded in increasingly subtle ways. The implications extend far beyond black holes themselves. If information can be destroyed, it suggests that the universe isn't as orderly and predictable as we thought. It would mean that perfect prediction is impossible, not just practically, but fundamentally, that the future might not be uniquely determined by the past. Recent advances in quantum computing and quantum information theory have opened new avenues for exploring these questions. Scientists are discovering that information and quantum entanglement might be more fundamental to reality than matter and energy themselves. In this view, black holes aren't just gravitational objects. They're quantum information phenomena that challenge our understanding of what information means and how it behaves. But this information paradox is just the beginning of black hole mysteries. As we probe deeper into their nature, we encounter paradoxes that seem to tear at the very fabric of spacetime itself. The firewall paradox, a cosmic controversy. Picture yourself approaching a black hole, drifting slowly toward that invisible boundary where physics gets strange. According to Einstein's general relativity, you shouldn't feel anything unusual as you cross the event horizon. Space should feel smooth and normal, like stepping from one room into another. But quantum mechanics tells a different story, one that's both beautiful and terrifying. The firewall paradox emerged from a simple question: what happens to quantum entanglement when one particle of an entangled pair falls into a black hole? In the quantum world, particles can be mysteriously connected across vast distances, sharing information instantaneously. But what happens when that connection is severed by an event horizon? Imagine two dancers performing a perfectly synchronized routine, even when separated by miles. Now imagine one dancer suddenly disappearing behind a curtain that no information can cross. According to quantum mechanics, the synchronization should continue, but the information paradox suggests it can't. Something has to give, and the proposed solution is both elegant and disturbing. The firewall hypothesis suggests that the event horizon isn't the smooth, invisible boundary we imagined. Instead, it's a wall of incredibly high-energy radiation, a firewall that would instantly incinerate anything trying to cross it. This solves the information paradox by preventing information from actually entering the black hole. But it creates a new problem. It violates the equivalence principle, one of the cornerstones of general relativity. Think of it like this. Einstein's theory says that falling freely should feel the same everywhere. Whether you're falling toward Earth or falling into a black hole, the firewall theory suggests that black holes are special, that they have this violent boundary that makes falling into them fundamentally different from falling anywhere else. But here's where the controversy deepens. Some physicists argue that the firewall is an illusion, a misunderstanding of how quantum mechanics and gravity interact. They propose that information doesn't disappear into black holes, but is instead reflected back, encoded in the Hawking radiation in ways so subtle we can't detect them with current technology. Others take an even more radical approach, suggesting that black holes might not have interiors at all. In this view, what we call a black hole is actually an incredibly dense, hot surface, a fuzzball of quantum strings and fields that only appears to have an interior from the outside. Information never crosses an event horizon because there's no interior to cross into. The debate has split the physics community into camps, each defending their interpretation with mathematical precision and philosophical passion. Some argue that the firewall is real, and that we need to abandon our cherished notions about smooth spacetime. Others insist that information must be preserved, and that firewalls are impossible. What makes this controversy particularly fascinating is that it's not just about abstract mathematics. It touches on fundamental questions about the nature of reality itself. Are space and time truly continuous, or are they made of discrete quantum units? Is information more fundamental than matter? Can the universe actually destroy information, or must it always find a way to preserve it? Recent experiments in quantum mechanics have begun to test some of these ideas. Scientists have created laboratory analogues of black holes using sound waves and condensed matter systems, observing how information behaves at artificial event horizons. While these experiments can't directly test the firewall hypothesis, they're providing new insights into how quantum information behaves under extreme conditions. The firewall paradox also highlights the deep connection between information theory and fundamental physics. It suggests that understanding black holes might require us to think more like computer scientists than traditional physicists, focusing on how information is processed and stored rather than just how matter and energy behave. Perhaps most intriguingly, the firewall paradox might be telling us that asking what's inside a black hole is the wrong question entirely. Maybe black holes are fundamentally about surfaces and boundaries, not interiors and volumes. Maybe they're teaching us that the universe is more like a hologram than we ever imagined, that the information we think is stored in three-dimensional space is actually encoded on two-dimensional surfaces. As we contemplate these cosmic firewalls, we're drawn to consider the black holes that aren't just theoretical constructs but real, massive objects that shape the very galaxies we live in. Supermassive giants at galactic hearts. In the center of our Milky Way galaxy, something extraordinary lurks in the darkness. It's invisible to our eyes, yet it's 4 million times more massive than our Sun. It's called Sagittarius A, pronounced A-star, and it's our local supermassive black hole, a gravitational giant that holds our entire galaxy together like a cosmic anchor. Imagine trying to comprehend something 4 million times more massive than the Sun. Our Sun could fit about 1.3 million Earths inside it. So we're talking about something that could contain quintillions of Earths. Yet this massive object is compressed into a space smaller than the orbit of Mercury. It's a concentration of matter so dense that it warps spacetime for thousands of light-years in every direction. But here's what's truly remarkable. Nearly every galaxy we've observed has one of these giants at its center. It's as if the universe has a standard architectural plan. Build a galaxy, install a supermassive black hole in the middle. This isn't coincidence. It's a fundamental feature of how galaxies form and evolve. These galactic giants aren't just passive anchors, they're active participants in galactic evolution, feeding on gas and dust that spirals into them, heating up and glowing brilliantly before disappearing forever. When they feed actively, they become quasars, some of the brightest objects in the universe, visible from billions of light-years away. A feeding supermassive black hole can outshine its entire host galaxy, powered by matter falling into an inescapable gravitational well. The relationship between a supermassive black hole and its galaxy is like a cosmic dance of mutual influence. The black hole's gravity helps shape the galaxy's structure, while the galaxy feeds the black hole with gas and stars. There's even a mysterious correlation. The more massive the black hole, the more massive the galaxy's central bulge of stars. It's as if they grow together, each influencing the other's development over billions of years. This relationship becomes even more intriguing when we consider that these black holes can regulate star formation across entire galaxies. When a supermassive black hole feeds actively, it can generate powerful jets of energy that heat up the surrounding gas, preventing it from cooling and condensing into new stars. In effect, these black holes can switch star formation on and off across regions hundreds of thousands of light-years wide. But how did these giants form in the first place? This question has puzzled astronomers for decades. Stellar mass black holes form when massive stars collapse, but there's no star massive enough to create a supermassive black hole directly. These giants must have grown over time, but the mechanism remains mysterious. One possibility is that they started as smaller seed black holes in the early universe, perhaps a few hundred times the mass of the Sun, and grew by feeding on gas and merging with other black holes. But calculations suggest this process would take longer than the age of the universe to create the supermassive black holes we observe in very distant, very young galaxies. Another intriguing possibility is that supermassive black holes formed directly from the collapse of massive gas clouds in the early universe. Without ever being stars, these primordial black holes might have been born supermassive, seeded by the universe's first gravitational instabilities. Recent observations have revealed that some supermassive black holes are spinning at incredible speeds, close to the theoretical maximum. This spin carries enormous energy and angular momentum, creating effects that ripple through spacetime itself. A spinning black hole drags space around with it, creating a region called the ergosphere, where space itself is forced to rotate. This rotation can be tapped for energy, potentially powering some of the most energetic phenomena in the universe. The study of these galactic giants has also revealed unexpected connections between black holes and the fundamental constants of physics. The mass of a galaxy's central black hole seems to be related to the speed of stars in the galaxy's outer regions, suggesting a deep connection between local gravitational effects and global galactic properties. Perhaps most remarkably, these supermassive black holes might be cosmic timekeepers, preserving records of their galaxy's entire history. Every star that falls in, every gas cloud that feeds them, every merger with another black hole, all of these events leave subtle signatures that might be detectable with future technology. As we observe these solitary giants, we're naturally drawn to consider what happens when they're not alone. When two of these cosmic monsters find each other across the vast darkness of space, binary black holes, and the dance of doom. Imagine two cosmic titans, each millions of times more massive than our Sun, locked in an eternal dance of gravity and space-time. They spiral around each other, getting closer and closer, their gravitational embrace growing tighter with each orbit. This isn't a gentle waltz. It's a dance of doom that will end in one of the most violent events the universe can produce. Binary black holes are exactly what they sound like. Two black holes orbiting each other, bound by their mutual gravitational attraction. But unlike binary stars, which can orbit each other for billions of years in stable configurations, binary black holes are doomed. They're losing energy constantly, radiating it away in the form of gravitational waves, ripples in spacetime itself that carry away orbital energy with each pulse. Picture spacetime as a calm pond, and these orbiting black holes as stones skipping across its surface. Each orbit sends waves rippling outward at the speed of light, carrying away energy and angular momentum. As energy is lost, the orbit shrinks, the black holes spiral closer together, and the gravitational waves grow stronger and more frequent. This process starts slowly. Over millions or billions of years, the two black holes gradually spiral inward, their orbits shrinking imperceptibly. But as they get closer, the process accelerates. The gravitational waves grow stronger, carrying away more energy, causing the orbit to shrink faster, which produces stronger waves, which carry away more energy. It's a runaway process that leads to an inevitable conclusion. In the final seconds before merger, the two black holes are orbiting each other hundreds of times per second, each moving at a significant fraction of the speed of light. The gravitational waves they produce are so strong that they stretch and compress space itself by amounts that, while tiny, can be detected by the most sensitive instruments humanity has ever built. The merger itself is almost impossible to imagine. Two regions of spacetime where the normal laws of physics break down somehow join together, creating a single, larger black hole. The event releases more energy and gravitational waves than all the stars in the observable universe produce in light. For a brief moment, the merger outshines the entire electromagnetic universe, not in light, but in gravitational waves. But here's what makes this dance particularly fascinating. We can now listen to it. The Laser Interferometer Gravitational Wave Observatory LIGO has detected dozens of these mergers, turning gravitational waves into sound waves that we can actually hear. Each merger has its own unique chirp, a characteristic sound that rises in pitch and volume as the black holes spiral together, ending in a brief sharp note as they merge. These detections have revolutionized our understanding of black holes. We've learned that binary black holes are far more common than we expected, that black holes can have a wider range of masses than we thought, and that some black holes are spinning much faster than theoretical models predicted. We've even investigated mergers between black holes and neutron stars, and between two neutron stars. The study of binary black holes has also revealed surprising details about how black holes form and evolve. Some of the black holes we've detected are too massive to have formed from stellar collapse alone, suggesting that black holes can grow through mergers much more efficiently than we thought. Others have spins that are difficult to explain with current formation models, hinting at new physics in the extreme environments where black holes are born. Perhaps most intriguingly, binary black holes might be cosmic archaeologists, preserving information about the conditions in the early universe. The black holes we detect today formed from stars that lived and died billions of years ago, when the universe was younger and the conditions for star formation were very different. By studying the masses and spins of merging black holes, we might be able to reconstruct the history of star formation and stellar evolution across cosmic time. The dance of binary black holes also raises profound questions about the nature of spacetime itself. During the merger, the two black holes don't just combine, they create a new configuration of spacetime that's unlike anything else in the universe. The event horizon of the resulting black hole has a complex dynamic shape that settles into a simple sphere only after the merger is complete. Some theoretical physicists suggest that binary black hole mergers might be windows into quantum gravity, the long-sought theory that unifies general relativity with quantum mechanics. The extreme conditions during a merger might produce effects that are impossible to observe anywhere else, potentially revealing new aspects of how spacetime behaves at its smallest scales. As we listen to these cosmic concerts, we're not just hearing the deaths of individual black holes, we're hearing the universe itself singing, its voice carried by the vibrations of spacetime, echoes in the fabric, gravitational waves. Close your eyes and imagine you could hear the universe itself, not the electromagnetic symphony of radio waves and light, but the deeper music of spacetime itself vibrate. For most of human history, we've observed the cosmos through light and its cousins, radio waves, X-rays, gamma rays. But now, for the first time, we're listening to the universe through gravitational waves, and it's teaching us things we never could have learned any other way. Gravitational waves are ripples in the fabric of spacetime itself, created when massive objects accelerate in just the right way. Think of spacetime as a vast invisible ocean, and massive accelerating objects as ships creating wakes that spread outward at the speed of light. These ripples are incredibly subtle. They stretch and compress space by amounts smaller than 1,000th of the width of a proton, yet they carry information about some of the most violent events in the universe. The first gravitational waves we detected came from a collision between two black holes that happened 1.3 billion years ago, when the most complex life on Earth was still single-celled. The waves traveled across the universe at the speed of light, carrying the story of that cosmic collision through space and time until they reached Earth on September 14, 2015, where they were detected by the LIGO Observatory. What's remarkable about gravitational waves is that they're completely different from electromagnetic radiation. Light can be blocked, absorbed or scattered by matter, but gravitational waves pass through everything almost unchanged. They carry information from the hearts of the most violent events in the universe, regions where matter is so dense and gravity so strong that light itself cannot escape. When we listen to gravitational waves, we're hearing the universe's most fundamental heartbeat. Each detected merger tells a story that unfolds over millions of years, compressed into a brief chirp that lasts seconds or less. We hear the slow orbital decay as two black holes spiral together, the rapid crescendo as they approach merger, and the final sharp note as they become one. But gravitational waves don't just tell us about individual events. They're revealing the hidden architecture of the universe itself. By detecting mergers at different distances, we're mapping the rate of cosmic evolution, learning how often these events occur and how they've changed over time. We're discovering that the universe is far more dynamic than we imagined, filled with colliding black holes and neutron stars creating a constant background of gravitational music. The detection of gravitational waves has also confirmed some of Einstein's most profound predictions about the nature of space and time. The waves arrive exactly as his theory of general relativity predicted, traveling at the speed of light and carrying energy away from the systems that create them. It's as if the universe is validating our deepest theories about its own structure. Perhaps most intriguingly, gravitational waves might carry information about the earliest moments of the universe itself. During cosmic inflation, the rapid expansion that occurred just after the Big Bang, the universe might have produced gravitational waves that are still propagating today. Detecting these primordial gravitational waves would be like hearing the universe's birth cry, preserved in the vibrations of spacetime for nearly 14 billion years. The study of gravitational waves is also revealing unexpected connections between seemingly unrelated phenomena. Some theoretical physicists propose that gravitational waves might be related to dark matter and dark energy, the mysterious substances that make up most of the universe. Others suggest that gravitational waves might carry information about extra dimensions, if they exist. Future gravitational wave detectors will be able to hear events that are currently beyond our reach. Space-based detectors like LISA will be sensitive to lower-frequency gravitational waves, potentially detecting the slow dance of supermassive black holes as they spiral together over millions of years. These observations might reveal how galaxies merge and how supermassive black holes grow over cosmic time. Ground-based detectors are becoming more sensitive, able to detect weaker signals from more distant events. Soon we might be able to hear gravitational waves from the collapse of individual massive stars, witnessing the birth of new black holes in real time. We might even detect gravitational waves from exotic objects like cosmic strings or primordial black holes, opening windows into physics beyond our current understanding. The field of gravitational wave astronomy is also developing new techniques for extracting information from these cosmic signals. By analyzing the polarization of gravitational waves, we might be able to test alternative theories of gravity. By studying how gravitational waves interact with intervening matter, we might learn about the structure of spacetime itself. As we tune our ears to the universe's gravitational music, we're naturally drawn to wonder what other invisible phenomena might be hiding in the cosmic darkness, waiting to be discovered. Can we see the invisible? Imaging a shadow. Imagine trying to photograph something that's completely invisible, something that swallows light so completely that it creates a shadow against the bright background of the universe. This seems impossible, yet that's exactly what the Event Horizon Telescope accomplished in 2019. It captured the first image of a black hole's shadow, transforming our understanding of these cosmic giants from theoretical constructs into visual reality. The image itself is almost poetic in its simplicity. A bright ring of glowing matter surrounding a dark, circular shadow, but within that shadow lies one of the most extreme objects in the universe, the supermassive black hole at the center of the galaxy M87, 6.5 billion times more massive than our Sun and located 55 million light-years away. Creating this image required turning the entire Earth into a telescope. The Event Horizon Telescope isn't a single instrument, but a network of radio telescopes scattered across the globe, from the South Pole to Hawaii, from Chile to Spain. By combining their observations using a technique called very long baseline interferometry, astronomers created a virtual telescope as large as Earth itself, the only instrument capable of seeing details small enough to resolve a black hole's shadow. The shadow see isn't the black hole itself, but rather the absence of light created by the black hole's event horizon. Around this darkness we see a bright ring of superheated matter, gas and dust, spiraling into the black hole at nearly the speed of light. This matter is so hot that it glows with the energy of billions of suns, creating a brilliant backdrop against which the black hole's shadow stands out like a dark silhouette. But the image reveals more than just the black hole's size and shape. The ring of light is brighter on one side than the other, a phenomenon called relativistic beaming. This occurs because the matter is moving so fast that the light from the approaching side is boosted and brightened, while the light from the receding side is dimmed. It's a direct visual confirmation of Einstein's special theory of relativity in action around a black hole. The shadow itself is about 2.6 times larger than the black hole's event horizon, a measurement that perfectly matches the predictions of general relativity. This size difference occurs because the black hole's gravity bends light around it, creating a gravitational lens that makes the shadow appear larger than the actual event horizon. It's as if the black hole creates a dark magnifying glass, enlarging its own shadow against the bright background. Creating this image required years of coordination and unprecedented international cooperation. Telescopes had to observe simultaneously, despite being separated by thousands of miles and operating in different time zones. The observations generated petabytes of data that had to be flown on hard drives to central processing centers. So much data that it was faster to physically transport it than to send it over the internet. The technical challenges were immense: atmospheric turbulence, equipment failures, and weather conditions at any of the telescopes could ruin the entire observation. The team had to develop new algorithms and computational techniques to process the data, essentially inventing new ways to create images from radio waves collected across the globe. But perhaps the most remarkable aspect of this achievement is what it represents for our understanding of black holes. For decades, black holes existed primarily in the realm of theory and mathematics, while we had indirect evidence of their existence. Stars orbiting invisible, massive objects, jets of matter streaming from galactic centers. We had never actually seen one. The Event Horizon Telescope changed that, providing direct visual evidence of these cosmic giants. The image also opens new avenues for testing our theories about gravity and spacetime. By comparing the observed shadow to theoretical predictions, astronomers can test whether general relativity accurately describes gravity in the extreme environment around a black hole. So far, Einstein's theory has passed these tests with flying colors, but future observations might reveal deviations that point to new physics. The success of the Event Horizon Telescope has inspired plans for even more ambitious projects. A space-based version could potentially image the black hole at the center of our own galaxy, Sagittarius A/Y, in much greater detail. Future observations might even be able to detect changes in the black hole's shadow over time, potentially revealing how these objects grow and evolve. The ability to image black holes also raises intriguing possibilities for studying fundamental physics. Some theories predict that black holes might have hair, small deviations from perfect spherical symmetry that could be detected in high-resolution images. Others suggest that the event horizon might have a complex structure that could be revealed through careful analysis of the shadow's shape. As we develop better techniques for seeing the invisible, we're naturally led to wonder about the black holes that might be hiding much closer to home, formed in the universe's earliest moments, primordial black holes, and the early universe. In the first fraction of a second after the Big Bang, when the universe was smaller than a grapefruit, but contained all the matter and energy that would eventually form billions of galaxies, something extraordinary might have happened. Tiny fluctuations in the cosmic density, quantum ripples in the primordial soup, might have collapsed under their own gravity to form the first black holes. These primordial black holes would be unlike anything we see today, born not from the collapse of stars but from the very turbulence of creation itself. Imagine the early universe as a vast ocean of energy and matter, far denser than the heart of any star. In this cosmic tempest, small regions that were slightly denser than average might have collapsed into black holes of all sizes, some as small as elementary particles, others as massive as mountains, and still others rivaling the mass of our sun. These primordial black holes would have formed when the universe was less than a second old, making them the universe's first compact objects. The idea of primordial black holes emerged from our understanding of cosmic inflation, the rapid expansion that occurred just after the Big Bang. During inflation, quantum fluctuations were stretched to cosmic scales, creating the seeds that would eventually become galaxies and galaxy clusters. But some of these fluctuations might have been so large that they collapsed immediately, forming black holes in the universe's first moments. Unlike stellar black holes, which form from the collapse of massive stars and have masses at least a few times that of our sun, primordial black holes could have formed with virtually any mass. The smallest would have been incredibly tiny, smaller than atoms but more massive than mountains. The largest might have been thousands of times more massive than our sun, rivaling the supermassive black holes we see at the centers of galaxies today. These primordial black holes would have had a profound impact on the early universe. The smaller ones would have evaporated quickly through Hawking radiation, potentially contributing to the cosmic microwave background radiation we observe today. The larger ones might have served as seeds for the first stars and galaxies, providing gravitational wells around which matter could collect and begin forming the universe's first structures. But here's where primordial black holes become particularly intriguing. They might still be with us today. While the smallest ones would have evaporated billions of years ago, larger primordial black holes could have survived to the present day. They might be scattered throughout the universe, invisible and undetectable, except through their gravitational effects. Some scientists have proposed that primordial black holes might account for some or all of the universe's dark matter, the mysterious substance that makes up about 85% of all matter, but doesn't interact with light. If primordial black holes are abundant enough, they could provide the gravitational scaffolding that shapes the large-scale structure of the universe, all while remaining completely invisible to our telescopes. The search for primordial black holes has led to some of the most creative detection methods in astronomy. Scientists look for gravitational lensing effects, the bending of light around massive objects, that might reveal the presence of these invisible companions. They study the formation of the first stars, looking for signs that they formed around primordial black hole seeds. They even analyze the dynamics of binary star systems, searching for evidence of invisible companions that might be primordial black holes. Recent advances in gravitational wave astronomy have opened new possibilities for detecting primordial black holes. The LIGO detectors have observed mergers between black holes with masses that are difficult to explain through stellar evolution alone. Some of these might be primordial black holes that formed in the early universe and are only now colliding after billions of years of cosmic evolution. The study of primordial black holes also provides insights into the fundamental nature of spacetime itself. These objects would have formed when the universe was so dense and hot that quantum effects might have been important, even on cosmic scales. Understanding how they formed and evolved could reveal new physics about the relationship between gravity and quantum mechanics. Perhaps most remarkably, primordial black holes might be windows into the multiverse. Some theories suggest that the quantum fluctuations that created these black holes might also have created bubble universes, separate regions of spacetime, with different physical laws. If this is true, then primordial black holes might be fossils of cosmic inflation, preserving information about the process that created our universe, and possibly others. The possibility that primordial black holes are abundant in today's universe raises intriguing questions about what might be lurking in our cosmic neighborhood. Are we surrounded by mini black holes? As you read these words, you might be surrounded by invisible companions. Tiny black holes, perhaps no larger than atoms but more massive than mountains, drifting silently through space, and even through your body. This isn't science fiction. It's a serious possibility that emerges from our understanding of the early universe and the nature of black holes themselves. These hypothetical mini black holes would be fundamentally different from their stellar cousins. Instead of forming from the collapse of massive stars, they would be primordial, relics from the universe's first moments, when matter was so dense that even small fluctuations could collapse into black holes. A mini black hole with the mass of Mount Everest would be smaller than a proton, yet its gravitational field would be intense enough to trap light and warp spacetime around it. The idea that we might be surrounded by these invisible objects emerged from Stephen Hawking's work on black hole evaporation. Hawking showed that black holes aren't perfectly black. They emit radiation and slowly evaporate over time. The smaller the black hole, the faster it evaporates. Black holes with masses less than a mountain would have evaporated completely by now, but those with masses greater than a mountain could still be around today. Think about what this means for our everyday experience. If mini black holes are abundant, they would be passing through Earth constantly, perhaps millions of them, every second. They would pass through the atmosphere, through the ground, through buildings, and even through our bodies without us noticing. Their gravitational effects would be far too weak to affect ordinary matter directly, but they would contribute to the overall gravitational field that shapes the universe on large scales. The search for mini black holes has led scientists to some of the most exotic corners of physics. These objects would be perfect laboratories for studying quantum gravity, the long-sought theory that unifies Einstein's general relativity with quantum mechanics. Near a mini black hole, the effects of quantum mechanics and gravity would be equally important, potentially revealing new physics that's impossible to study anywhere else. Some theoretical physicists have proposed that mini black holes might be created artificially in high-energy particle collisions. When particles collide at extreme energies, They might create regions of space so dense that they collapse into tiny black holes. These laboratory black holes would evaporate almost instantly, but they might reveal important information about the nature of gravity at quantum scales. The possibility of artificial black hole creation has raised both excitement and concern. On one hand, it could provide unprecedented insights into fundamental physics. On the other hand, it raises questions about safety. Could an artificially created black hole somehow grow and pose a threat? Current calculations suggest that any mini black holes created in particle accelerators would be far too small and would evaporate far too quickly to pose any danger, but the questions highlight our incomplete understanding of these exotic objects. Mini black holes might also play a role in some of the universe's most mysterious phenomena. Some scientists have suggested that dark matter, the invisible substance that makes up most of the universe's mass, might consist partially or entirely of primordial black holes. If this is true, then the dark matter that shapes galaxies and galaxy clusters might actually be composed of countless tiny black holes, each one a gravitational fossil from the universe's first moments. The study of mini black holes also connects to some of the deepest questions in physics. If these objects exist, they would be quantum mechanical objects that create classical gravitational effects. Understanding how they work might reveal fundamental truths about the nature of space, time, and matter itself. Recent developments in string theory have suggested that mini black holes might be more common than we thought. In theories with extra dimensions, the strength of gravity might be much stronger at short distances than we observe in our everyday world. If this is true, then mini black holes might form more easily and be more abundant than current estimates suggest. The search for mini black holes continues through multiple approaches. Scientists study the cosmic microwave background radiation, looking for distortions that might have been caused by primordial black holes in the early universe. They analyze the motion of stars and galaxies, searching for gravitational effects that might reveal the presence of invisible compact objects. They even study the light from distant quasars, looking for gravitational lensing effects that might indicate mini black holes passing in front of them. As we contemplate the possibility that we're surrounded by these invisible gravitational mysteries, we're naturally drawn to consider their relationship to an even more mysterious component of our universe: black holes versus dark matter, a hidden connection. In the vast cosmic web that spans the universe, two of the most mysterious phenomena seem to exist in different realms entirely. Dark matter, the invisible scaffolding that holds galaxies together, appears to be everywhere but interact with nothing. Black holes, meanwhile, are localized gravitational monsters that devour everything in their path. Yet recent discoveries suggest these seemingly opposite phenomena might be more connected than we ever imagined. Picture the universe as a vast, invisible architecture. Dark matter provides the framework, the invisible beams and supports that hold everything together. It outweighs ordinary matter by a factor of 5, yet it doesn't emit, absorb, or reflect light. We know it exists only because of its gravitational effects. Galaxies rotate faster than they should. Galaxy clusters move in ways that ordinary matter alone cannot explain, and the cosmic microwave background shows patterns that require dark matter to form. For decades, scientists have assumed that dark matter consists of exotic particles, theoretical entities with names like WIMPs, weakly interacting massive particles, or axions. These particles would interact with ordinary matter only through gravity, making them nearly impossible to detect directly. Enormous experiments deep underground search for these particles, but so far they've remained elusive. But what if we've been looking in the wrong place? What if dark matter isn't made of exotic particles at all, but rather of something we already understand: black holes? This possibility emerged from our growing understanding of primordial black holes, those cosmic fossils that might have formed in the universe's first moments. Unlike stellar black holes, which form from the collapse of massive stars, primordial black holes could have formed with a wide range of masses, from microscopic to stellar and beyond. Most importantly, they could have formed in the quantities needed to account for dark matter. The idea is elegantly simple. If the early universe was turbulent enough to create vast numbers of primordial black holes, these objects could provide the gravitational effects we attribute to dark matter. They would be invisible to electromagnetic radiation, just like dark matter. They would cluster around galaxies and galaxy clusters, providing the gravitational scaffolding that shapes large-scale structure. And they would have been present from the universe's earliest moments, explaining why dark matter effects are observed in the most distant galaxies. Recent observations have lent support to this possibility. The LIGO gravitational wave detectors have observed mergers between black holes with masses that are difficult to explain through stellar evolution. Some of these black holes might be primordial, formed in the early universe rather than from stellar collapse. If primordial black holes are common enough to produce the merger rate LIGO observes, they might also be common enough to constitute dark matter. But the connection between black holes and dark matter might go even deeper. Some theoretical physicists propose that black holes and dark matter might be different manifestations of the same underlying phenomenon. In theories with extra dimensions, for example, ordinary matter might appear as dark matter when viewed from higher dimensional space, while what we perceive as black holes might be higher dimensional objects intersecting our three-dimensional world. The relationship between black holes and dark matter also appears in the study of galactic centers. Nearly every galaxy has a supermassive black hole at its center, and the mass of this black hole is closely correlated with the mass of the galaxy's dark matter halo. This correlation suggests a deep connection between the formation and evolution of black holes and the distribution of dark matter. Some scientists have proposed that dark matter might actually be created by black holes. In this scenario, black holes don't just consume matter, they produce it, creating streams of dark matter particles through exotic quantum processes. This would explain why dark matter is so abundant and why it's distributed in the patterns we observe. Others suggest that black holes might be windows into the dark sector, a hypothetical realm of physics where dark matter particles interact with each other through forces we haven't discovered yet. In this view, black holes might be the only objects that can bridge the gap between ordinary matter and dark matter, providing a mechanism for the two to influence each other. The study of black holes and dark matter together has also revealed unexpected connections to other cosmic mysteries. Dark energy, the mysterious force that's accelerating the expansion of the universe, might be related to both black holes and dark matter. Some theories suggest that the vacuum energy around black holes might contribute to dark energy, while others propose that dark matter and dark energy are different aspects of the same phenomenon. Future observations might reveal more about this hidden connection. The James Webb Space Telescope is studying the earliest galaxies, looking for clues about how dark matter and black holes co-evolved in the universe's youth. Gravitational wave detectors are becoming more sensitive, potentially revealing whether primordial black holes are common enough to constitute dark matter. And new particle physics experiments continue to search for dark matter particles, potentially ruling out or confirming exotic particle theories. As we probe deeper into these cosmic mysteries, we're naturally drawn to consider even more profound questions about the nature of reality itself. Could black holes spawn new universes? Imagine that every black hole in our universe is not an end, but a beginning. A cosmic seed that gives birth to an entirely new universe, complete with its own space, time, and physical laws. This isn't just science fiction, it's a serious theoretical possibility that emerges from our deepest understanding of gravity, quantum mechanics, and the nature of spacetime itself. The idea emerges from a fundamental puzzle about black holes. What happens at the singularity? In the center of every black hole, according to general relativity, lies a point where matter is compressed to infinite density and spacetime curvature becomes infinite. But infinity is a red flag in physics. It usually signals that our theories are breaking down and new physics is needed. Some theoretical physicists propose that instead of forming a singularity, the matter inside a black hole might bounce back, creating a new expanding region of spacetime, effectively a new universe. This big bounce would be hidden from our view behind the event horizon, making it impossible for us to observe directly, but it would be just as real as our own universe. Think of it like this. If you could somehow survive the journey into a black hole and travel to its center, you might not find a singularity at all. Instead, you might find yourself in a new universe, with its own three-dimensional space expanding from what we would call a white hole, the time-reversed version of a black hole that spews matter out instead of swallowing it. This possibility is supported by some remarkable mathematical similarities between black holes and the Big Bang. Both involve extreme densities and curvatures of spacetime. Both mark boundaries beyond which our normal understanding of physics breaks down, and both might be different sides of the same cosmic coin. Black holes might be the other side of Big Bang events, connected through regions of spacetime that are hidden from our view. The universe-spawning black hole theory also offers potential solutions to some of cosmology's biggest puzzles. Why does our universe have the particular physical constants it does? If black holes create new universes with slightly different physical laws, then we might be living in a vast multiverse, where countless universes are being born constantly. Our universe would have the physical constants it does, because those constants allow for the formation of stars, black holes, and ultimately, conscious observers like us. This idea connects to the concept of cosmic natural selection, proposed by theoretical physicist Lee Smolin. In this scenario, universes that are good at producing black holes would have more offspring universes, while universes that produce few black holes would have fewer descendants. Over many generations, this process might select for universes with physical constants that favor black hole formation, and coincidentally, the formation of stars, planets, and life. The mathematics of this theory is surprisingly elegant. The equations that describe the interior of a black hole can be transformed into equations that describe an expanding universe. The Big Bang might not be the beginning of time, but rather the other side of a black hole collapse in a parent universe. This would mean that time doesn't have a beginning or end, but rather forms a more complex structure, where universes give birth to other universes in an eternal cosmic cycle. But if new universes are being born inside black holes, what does this mean for information? The information paradox. The puzzle of what happens to information that falls into a black hole might be resolved if that information is not destroyed, but rather becomes part of the initial conditions for a new universe. In this view, black holes are not information destroyers but information processors, transforming the complexity of one universe into the initial conditions for another. The theory also raises profound questions about the nature of reality itself. If we're living inside a black hole in a parent universe, then what we call the observable universe might be just a small portion of a much larger reality. The cosmic microwave background radiation, the afterglow of the Big Bang, might actually be the distorted view of the parent universe, as seen from inside the black hole. Some versions of this theory suggest that we might be able to detect signs of our parent universe. Quantum fluctuations in the cosmic microwave background might carry information about the conditions in the parent universe. Gravitational waves might propagate from the parent universe into our own, carrying signals from cosmic events that occurred before our Big Bang. The possibility of universe spawning black holes also connects to our understanding of quantum mechanics and gravity. If black holes can create new universes, it suggests that spacetime itself might be quantized, made up of discrete units rather than being continuous. This would have profound implications for our understanding of space-time and the fundamental nature of reality. As we contemplate the possibility that our entire universe might be the interior of a black hole in some larger reality, we're naturally drawn to consider the ultimate question about our cosmic situation. What if the universe is inside a black hole? Take a moment to consider the universe around you, the vast expanse of space filled with stars, galaxies, and cosmic mysteries stretching to the horizon of the observable universe. Now imagine that all of this, everything we can see and everything we can't, might be contained within the interior of a black hole in some larger parent universe. This mind-bending possibility emerges from the deepest mathematical connections between black holes and cosmology, and it might fundamentally change how we understand our place in reality. The idea begins with a simple observation. The observable universe has a finite size and age. We can see about 93 billion light-years in any direction, the distance light has traveled since the Big Bang, accounting for the expansion of space. Beyond this cosmic horizon, we simply don't know what exists. But what if this horizon isn't just a limitation of our observations but an actual boundary? Specifically, the event horizon of a black hole. The mathematics are surprisingly supportive of this possibility. If you calculate the mass contained within the observable universe and ask what size black hole would have that mass, the answer is remarkably close to the actual size of the observable universe. It's as if the universe is balanced right at the edge of being its own black hole, suggesting that maybe it actually is one. This connection becomes even more intriguing when we consider the expansion of the universe. From our perspective inside the universe, space appears to be expanding, carrying galaxies away from each other at ever-increasing speeds. But from the perspective of an outside observer, this expansion might look very different. It might appear as matter falling into a black hole, with the expansion we observe being the result of our warped perception of space and time near the event horizon. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, might actually be the distorted view of the parent universe as seen from inside the black hole. The nearly uniform temperature of this radiation with its tiny fluctuations might be the scrambled information about the conditions in the parent universe, processed through the extreme physics of black hole formation. If we're inside a black hole, it would explain some of the universe's most puzzling features. Why does the universe appear to be fine-tuned for life, with physical constants that seem perfectly adjusted to allow for stars, planets, and complexity? If our universe is one of many being born inside black holes, then we might be living in a cosmic lottery winner, a universe with the right conditions for observers like us to exist and wonder about their circumstances. The theory also offers a potential resolution to the Big Bang singularity problem. Instead of space-time beginning at a mathematical point of infinite density, the Big Bang might be the other side of a black hole collapse in the parent universe. Time wouldn't have a beginning. It would be part of a more complex structure, where universes give birth to other universes in an eternal cosmic cycle. This perspective changes how we think about the fundamental nature of space and time. If we're inside a black hole, then our three-dimensional space might be a kind of holographic projection of information stored on the two-dimensional surface of the event horizon. This connects to the holographic principle, one of the most profound ideas in modern physics, which suggests that all the information in a volume of space can be encoded on its boundary. The possibility that we're inside a black hole also has implications for the future of our universe. Instead of expanding forever and eventually experiencing heat death, our universe might eventually reach some kind of equilibrium state characteristic of black hole interiors. Or perhaps the expansion we observe is actually the early stages of a much more complex process that will eventually lead to the formation of new universes within our own black holes. But if we're inside a black hole, does this mean we're trapped forever? Not necessarily. Some theories suggest that black holes might be traversable, that they might contain wormholes or other structures that allow travel between different regions of space and time. If this is true, then our universe might be connected to other universes through a cosmic network of black holes and wormholes. The idea also raises questions about causality and information. If we're inside a black hole, then everything we do and everything we are might be determined by the initial conditions of the black hole's formation in the parent universe. Yet, from our perspective, we experience free will and the ability to make choices that affect the future. This suggests that the nature of causality might be more complex than we currently understand. Testing this theory is extremely challenging because by definition we can't see outside our own universe to confirm whether we are inside a black hole, but there might be subtle signatures we could detect. The cosmic microwave background might contain patterns that reflect the structure of the parent universe. Gravitational waves might propagate from the parent universe into our own, and the distribution of matter and energy in our universe might reflect the conditions of the black hole collapse that created us. As we contemplate the possibility that our entire reality might be contained within a black hole, we're naturally drawn to consider what all these mysteries teach us about the nature of existence itself. What black holes really teach us about reality. After our journey through the cosmic mysteries of black holes, we find ourselves in a curious position. We've explored invisible giants that shape galaxies, listened to the space-time vibrations of their cosmic dances, and contemplated the possibility that our entire universe might exist within one. But perhaps the most profound lesson black holes teach us isn't about gravity, or space-time, or even the universe itself. It's about the nature of knowledge and the beautiful mystery of existence. Think about what we've discovered. Black holes challenge every intuition we have about reality. They're invisible, yet observable, destructive yet creative, simple yet infinitely complex. They exist at the intersection of our most fundamental theories about space, time, matter, and information. They force us to question assumptions we didn't even know we were making about the nature of existence itself. Consider the information paradox. The puzzle of what happens to information that falls into a black hole. This isn't just a technical problem for physicists. It's a fundamental question about whether the universe is deterministic, or whether information can truly be destroyed. The answer affects how we understand causality, free will, and the very nature of reality itself. Or consider the firewall paradox, which asks whether the boundary of a black hole is smooth or violent. This seemingly abstract question touches on whether space and time are continuous or discrete, whether gravity and quantum mechanics can be reconciled, and whether our everyday experience of smooth space-time is an illusion covering up a more complex underlying reality. Black holes also teach us about the limits of knowledge itself. There are fundamental barriers to what we can know about these objects. We can never directly observe what happens inside an event horizon. We can never perform experiments at the singularity. We can never travel to a black hole and return to tell the tale. Yet this doesn't stop us from learning about them. It just forces us to be more creative about how we seek knowledge. The study of black holes has revolutionized our understanding of the relationship between gravity and quantum mechanics. These objects exist at the boundary between the classical world of general relativity and the quantum world of atomic physics. They suggest that space-time itself might be quantized, that information might be more fundamental than matter and energy, and that the universe might be more like a vast computer than a mechanical clockwork. Perhaps most remarkably, black holes have taught us about the holographic nature of reality. The holographic principle, the idea that all the information in a volume of space can be encoded on its boundary, emerged from the study of black holes. This principle suggests that our three-dimensional experience of space might be a kind of projection from a two-dimensional surface, fundamentally changing how we think about the nature of space and dimension. Black holes also reveal the deep connections between seemingly separate phenomena. They connect gravity to thermodynamics, showing that black holes have temperature and entropy. They connect classical physics to quantum mechanics, demonstrating that these two great theories of physics must somehow be unified. They connect the very large to the very small, showing that understanding cosmic giants requires insights from quantum mechanics. The search for black holes has also pushed the boundaries of human technological capability. From the gravitational wave detectors that can sense distortions smaller than 1,000th of a proton's width, to the planet-sized telescope arrays that can image the shadow of a black hole, these objects have inspired some of our species' greatest technological achievements. But perhaps the most profound lesson black holes teach us is about the nature of mystery itself. Despite decades of study, despite Nobel Prize-winning discoveries, despite images of their shadows and recordings of their mergers, black holes remain fundamentally mysterious. They remind us that the universe is far stranger and more wonderful than we can imagine, and that the most important questions might not have simple answers. Black holes teach us that reality is not what it seems. Space and time, which appear so solid and fundamental to our everyday experience, are actually dynamic and malleable. Matter and energy, which seem so substantial, might be emergent properties of something more fundamental. Even existence itself might be more complex than we assume. We might be living inside a black hole, or in a universe that gives birth to other universes through black holes. They also teach us about the beauty of the unknown. The fact that black holes exist at all is remarkable. Nature has found a way to create objects so extreme that they challenge our understanding of physics itself. They represent the universe's capacity for surprise, for complexity, for phenomena that exist at the very limits of what's possible. As we conclude our journey through the mysteries of black holes, we're left not with answers, but with better questions. What is the true nature of space and time? How does information behave in extreme gravitational fields? What happens at the boundary between the quantum and classical worlds? These questions don't have simple answers, but they point us toward a deeper understanding of reality itself. Black holes remind us that the universe is not just larger than we imagine, it's stranger than we can imagine. They teach us that mystery isn't something to be eliminated, but something to be celebrated, that the unknown isn't empty space, but fertile ground for discovery. They show us that the most profound truths about reality might be found not in the familiar world of everyday experience, but in the extreme conditions where our theories break down and new physics begins. In the end, black holes teach us that reality is far more interesting than we ever dared to hope. They invite us to expand our imagination, to question our assumptions, and to remain humble before the vast mystery of existence. They remind us that we are part of a universe that is not just vast and ancient, but creative and surprising, full of phenomena that challenge our understanding and inspire our wonder. And perhaps that's the greatest lesson of all, that the universe is not just something to be understood, but something to be marveled at, something that rewards our curiosity with ever deeper mysteries and ever greater beauty. Black holes don't just teach us about gravity or space-time. They teach us about the joy of discovery and the endless capacity of reality to surprise and delight us. As we drift off to sleep tonight, we can imagine ourselves floating through this cosmic wonderland, surrounded by invisible giants and gravitational waves, carried by the gentle current of expanding spacetime toward whatever new mysteries await us in the vast, beautiful, and endlessly surprising universe we call home.